From the lecture on coupled heat and moisture transport, we show three different parts. And the first part was that we demonstrated how we, with three equations, could calculate transient heat flow, isolated scene. But now we'll look more into the couplings, and we do that by first talking about similar equations, but for moisture flow. And like we had for heat, here we also have three types of equation: a transport equation, and I should say for moisture, we consider here, for illustration purposes, only vapor diffusion by fixed law. Then we will make a balance for where does the moisture go. So we should look to a continuity, keep track of the moisture. And we have two different equations that use different parameters, and we need a third type of equation, an equation of state, we can call it, to gather the first and the second equation together in order to make possibilities to make transient calculations. So let's move into it with the moisture. And like when we talked about for heat, we had Fourier's law to govern heat flow. Then for vapor diffusion, it's fixed law. And here it's the vapor pressure that is the driving potential that drives the, or gradients in the vapor pressure that drives the vapor flux. So vapor flux is the value G here, so kilograms per square meter and per second. And the material property to govern this, that's the vapor permeability, delta V, V for vapor. And we consider flux, which is per area, so in total we have a certain area that is somewhere in the middle of a material you can think of where we can look to this flux. That was our transport equation, the first type of equation. The next equation we should look to, that was the continuity, and that is to look to a box, again with surfaces like before, but now a surface on the left-hand side and on the right-hand side, where we have the flux we just calculated coming in on the left, and the same flux leaving on the right, plus an increment depending on how far we've gone along the width of the volume we're looking into here, a small dx, a small width we have there. We look again to the surface area of that segment of the material. We have the vapor pressure that we keep track of as the driving potential, and we should look to the balance of the moisture, and for that we look to moisture content in the unit kilograms per kilo as we use it here for moisture. Excuse me. So our balance equation says that if we have some flux coming in and another flux coming out, then per time, or in a unit of time, dt, then we'll have an increment in the amount of moisture in that material. And the amount of moisture mass of water is the mass of the dry material times that moisture content, or an increment in moisture content, those kilograms per kilos we introduced before. And the dry mass of the material, that's the dry mass, the dry density of the material, times the volume of the material. And the volume of the material, that's the surface area, times that thickness dx. So that increment in moisture content comes as a result of the difference between what comes in of flux on the left and what is going out on the right-hand side, so that we can look up here. And we multiply with that increment in time, dt, as we're talking about, and with the area, the transmission area for the flow. Excuse me again. So now we clean up this a little bit here. So we start up here and we take what we have. We eliminate a times dx that we had here and there. We have the two GVs we have removed also. So all what is left now here is rho and du on the left-hand side, and on the right-hand side we have the gradient of the fluxes here, and then multiply with the time increment dt. And then the fluxes gv that we had from our first equation, so we can insert now a fixed law. So gv was the gradient of vapor pressure times the vapor permeability. There was a minus sign in the fixed law, and there's also a minus sign here, so they are also eliminating one another. So here we have our continuity equation, but it has on the left-hand side that we keep track of moisture content, and on the right-hand side things are driven by the water vapor pressure. Now, in order to collect these changes in moisture content and in water vapor pressure, then we should work with this, what we call fundamentally an equation of state. But the equation is actually a graph, as I'll show you here. It's the absorption curve, the curve that tells for a certain relative humidity in the pores, in the material, what is in equilibrium, the moisture content U, as a weight percent in the material of moisture. And we're looking to changes. So therefore, we are interested to know if we have a change in relative humidity, how much change will we have in the moisture content. And for that, we use, for that change, those two between them, then we have the so-called moisture capacity, the Greek letter Xi. For relative humidity, we use the Greek letter phi to express as a variable there. So that's how it comes up here. And we're going to use it now, but remind you how we have Xi to tell us about this, the change of the U in relationship to the phi. Now, that means that from the equation before, well, we can work with phi, actually. We used to work with vapor pressure, but vapor pressure, that is the relative humidity times the saturation vapor pressure. And the saturation vapor pressure is something that is determined only by the temperature. So there's a potential for some coupling there between vapor pressures and temperatures, as we'll see. Now, if we, at first, on this slide, we're looking to isothermal conditions. So yes, we must know the temperature, but we assume it's constant, it's isothermal. And that means that this saturation vapor pressure, it's a constant we can determine at that temperature at which we are. And then this becomes only the gradient of phi in our equation here. So then we have what we used to have the gradient in vapor pressure in Fick's law, we can now express with the gradient in phi. And that means that when we look to the phi dx, if we want to express that as something that we had from our previous slide that we kept track of, which was the moisture content in our equations, let's see if we express phi instead, gradients of phi in gradients of moisture content. Well, that we can do by saying instead of the phi dx, that's the phi du times du dx. So we have now the gradient of the moisture content. But what we have here, the phi du, that was exactly what we had from our absorption curve. That was 1 over the what we called the moisture capacity Xi. So then we can clean up all these things here. We can express it in terms of the moisture content U. So we have the gradient of moisture content with time that we got from our equation of state. Well, for that we can insert, on the right-hand side, we can insert these transports that we get here driven by the gradient of the moisture content. And gathering all the parameters we had from before, they can all be gathered in one property here, which we call the moisture diffusivity. And the moisture diffusivity, if we look to the definitions from this slide and from the previous slide, the moisture diffusivity comes here as the permeability times the saturation vapor pressure divided by the density of the material and this moisture capacity Xi. So as a diffusivity, it has always the unit square meters per second. So that was our water vapor diffusivity. But this was for isothermal conditions. And guys, I promised you to show it with some couplings. So what happens if we have varying temperatures? So there is not only a moisture gradient across the material, but at the same time also a temperature gradient. And that I will now reveal in this system of defining things on the last slide here. So we write everything again. We start the same way. The gradient of vapor pressure we express as phi times the saturation pressure that we take the gradient of. And now we should consider that the saturation vapor pressure, since it's temperature dependent, and we could have a temperature gradient, well then we should take separately that there could be gradients of the saturation vapor pressure and gradients of the phi. So we take these gradients separately in our differentiation of a product as we have up here. Now it's plotted down here in red. Everything that is, of course, temperature dependent and everything that's moisture dependent is in blue. And what is temperature dependent? That was how the saturation vapor pressure was temperature dependent. So we should consider the PV as dt, and then we can take the gradient of the temperature to give us that gradient. Also, there is a small effect, I should say, but it's there in principle, whereby the absorption curve, we call it sometimes absorption isotherm. So at different temperatures, we have slightly different positions for the curve. So for a specific moisture content, at a different temperature, there would be a different equilibrium phi, relative humidity. So therefore, there is a small effect here also about how the curve is temperature dependent. That should also be considered as a secondary issue. Then, what we have from the slide just before, we have the same thing again, how vapor pressure is moisture content varying and how we use the moisture capacity, Xi, to express that. So all that comes together now in this more advanced equation where we consider both the temperature and the moisture effects. We clean it up like before and introduce, again, some diffusivities. So we had in blue, like before, we had the moisture diffusivity, but also we have a thermal vapor diffusivity. So all those coefficients here that are the TGX driven, we can comprise in a variable we call that thermal vapor diffusivity. And here you see the definition of the thermal vapor diffusivity. So now we have set up a set of equations whereby we can calculate a coupled vapor and temperature flow in our material. And here are this was looking to the moisture flow and how we introduce water vapor diffusivity and the thermal vapor diffusivity, as I've explained to you. Thank you for listening in to this.